Hi class, this is part 1 of section 3.5, transformation of functions. All right, so we're going to start with the graph of y equals x squared. So this is the parabola that we're hopefully all familiar with. And let's use this to graph the new function g of x is equal to x squared minus 2. So notice that the y values all decreased by 2. And the graph was shifted down 2 units. Next, let's graph y equals x squared plus 1. Here the graph shifted up 1 unit. Okay, so adding 1 moved the graph up, and subtracting 2 moved the graph down. So that's just what we would think, right? Adding is going to make our graph shift up, subtracting will make the graph shift down. Okay, let's go back to y equals x squared. And now let's look at h of x is equal to x minus 3 quantity squared. So now that minus 3 is with the x. So I picked some x values on my table, but I actually center them around 3, because if I let x equal 3, I would have 3 minus 3, or 0, here inside the parentheses. So that's where what's called the vertex of my parabola goes, that low point. So that shifted to the right 3 units, and then I picked 2 points on either side. So when we look at h of x is equal to x minus 3 quantity squared, that minus 3 actually makes the graph shift to the right 3 units. So it's kind of the opposite of what we might think. All right, next let's look at the graph of y equals x plus 2 quantity squared. So adding 2 to the x, again, it's going to be the opposite. So you might think adding 2 is going to move it to the right. It actually moves our graph to the left. So that vertex is now at negative 2, 0, because if I let my x equal negative 2, I'd have negative 2 plus 2, which is 0 squared. So that's how I get my low point. Okay, so in this slide, we have horizontal changes, right? Moving the graph to the right or to the left. So remember that the horizontal change is always the opposite of what you might think. So subtracting 3 actually moved the graph to the right, adding 2 moved the graph to the left. Okay, so now let's look at this curve. And we want to look at 2 times f of x, and then also f of 2 times x. Okay, when the 2 is outside, that's going to be a vertical change. So just like that very first example where we moved our graph up or down. Okay, here that 2 is outside, it's going to be a vertical change. It is going to vertically stretch our graph by a factor of 2. So instead of the graph having a high at 1 and a low at negative 1, it'll go all the way up to 2 and down to negative 2. Notice the points where the graph was crossing the x-axis. The y value was equal to 0 there, so multiplying by 2 doesn't affect it. It's still equal to 0. Okay, so we see that we're going to get a vertical stretch. And there's the graph of y equals 2 times f of x. Okay, and now we want to graph the one in green, f of 2 times x. So when the constant is with the x, it's going to be a horizontal change. And the horizontal changes are always the opposite of what you might think, right? So adding, we actually go to the left, subtracting, we go to the right. Here, multiplying by 2, it doesn't stretch it, but instead it's going to compress it or shrink the graph. Okay, so it's going to compress it by a factor of a half. So it's almost like this graph is going through that same cycle faster. Okay, but it only has to get to 1/2, whereas before in the black curve, we were all the way out at 1 when you went up and came back down. Okay, now we're going to look at the absolute value function, so our v function. And we want to see what the negatives are going to do. So let's look at h of x is the opposite of f of x, okay, or the opposite of the absolute value of x. Okay, so that negative is out front. and that's going to reflect our graph about the x-axis. So now instead of a V opening up, we have the V shape opening down. What if the negative is with the x? Okay, so in this case, since we're taking the absolute value of negative x, the graph will actually stay exactly the same. Our graph was reflected about the y-axis. However, the original graph was symmetric with respect to the y-axis, so reflecting it about the y-axis did not change the shape of the graph at all. Okay, when this happens, it means that we have an even function. Okay, so if the graph is symmetric with respect to the y-axis, the function is said to be an even function. So here are 3 examples of graphs that are symmetric to the y-axis. So these are all even functions. 2 of them we're familiar with, hopefully, right? Y equals x squared, and g of x is equal to 1 over x squared. Okay, both of those are part of the toolbox kit that we looked at earlier. Okay, those 2 graphs are symmetric to the y-axis. And then just here's another example of another function that is symmetric to the y-axis. Other functions will be symmetric to the origin. Okay, and if this is the case, then the function is said to be odd. All right, so f of x is equal to x cubed is one that we've seen before. Also, g of x is equal to 1 over x. And then here, this h of x is just a new function, just to give you more examples of functions that are symmetric to the origin, which means that, graphs that are symmetric to the origin, which means the functions are odd. When you're looking at symmetry, think of it as folding the graph twice. So once over the y-axis and then also over the x-axis. Okay, so if you do that and the 2 pieces match up, then your graph is symmetric with respect to the origin. All right, if you do have a graph that is symmetric to the x-axis, it's actually not going to be a graph of a function, right? So these graphs all fail the vertical line test. So we're not even discussing anything that's symmetric to the x-axis, okay, because we want to deal just with functions. Okay, so we will talk more about even and odd functions later, but we want to focus now on transformations. Okay, so we had what are called rigid transformations. So this is when the shape of the graph stays the same. So that's if you just move your graph up, down, right, or left. Okay, also reflecting it, so reflecting about the x-axis or the y-axis, those are all what are called rigid transformations. The other type of transformation, non-rigid, changes the shape of the graph. So this is if you have a vertical stretch or compression or a horizontal stretch or compression. Okay, so notice for the vertical changes, the plus c or minus c is kind of after the f of x. Here, vertical stretch or compression, that times c is in front of the f of x. For the horizontal changes, plus c or minus c is with the x, and here the c times x is with the x. Okay, so any horizontal change, first of all, it's going to be the opposite of what you might think. And then secondly, that c, the constant, is with the x. Vertical changes are just what you think. Adding, you go up, subtracting, you go down. Okay, and then the c is outside or away from the f of x. Okay, so we're going to look at more examples of this in the next 2 videos.